Okay, now in this section I'm gonna talk about in fact the encoding of the Mistral, which is called RoPE or Rotary Positional Encoding, and as you can see it is right here in the architecture of it, just these little circular symbols, and what will happen, we will add them and apply them on top of a query and key. But yeah, let's see what are they and how they work. So technically we have two main kinds of encodings, which one of them is the simple positional encoding or sinusoidal encoding, which mainly is being used in transformers, original transformers in Vaswani et al. But the RoPE or Rotary Positional Encoding is mainly used in more modern language models like LLaMA, GPT, DeepSeek, and Mistral as well. So it is much stronger in terms of maintaining relative positions and also long context, which is very useful in these language models because we want to have larger context window, and also it scales better. And the way that it works is, so in the previous version, in the simple version, it is just adding sinusoidal vectors, learned vectors, but here we rotate the Q and K vectors using the complex numbers and complex exponentials, and we will see what that means in a minute. And yeah, just it's a little bit harder to understand maybe because of its implementation, but we will dive deep into that and we'll see that how it exactly works. So yeah, feel free to have a look at its paper, RoPE or Rotary Positional Encoding, and on the paper, this is technically the final equation that we have for Rotary Positional Encoding. But what this exactly means, and if you want to have a look at how we get here and how we finally arrived to this kind of equation, you just have a look at the paper. I'm not going to explain it here. It is a little bit more detailed than what I want to do here. So yeah, what this means is technically it is just the rotation with the frequency vectors of theta in the position of the M, and this D means the dimension of the embedding. So technically what we have is, imagine that we have a sentence which contains of WI's, and each W is just, let's say, a word in the ith element word, and we have also the embedding of each of those words, or the, let's say, not embedding, yeah, we can say embedding of the token, which the dimension would be D here, and the thetas, or the frequencies we can call them, or angles, are just the length of the vector is half of the dimension, and we will find out why is this happening. It is from theta 1 all the way up to theta d over 2, and the way that we calculate them, those thetas, is just theta I would be 10,000, and this 10,000 is the constant. We can change it, but usually on the code it is 10,000 to the power of this whatever that it is. As I mentioned, the D is the dimension vector, embedding dimension, M is token position index, and XI, each of the XI's are the dimensional word embedding of the ith token. Okay, but this might be a little bit overwhelming, and how we can literally calculate this on Python code. It might be a little bit, might look a little bit hard and overwhelming, but there is a really good trick that how we can turn this into much easier format and much optimized format and calculate it. Just to give you a hint before diving deep into that, just imagine if we select each of these pairs, this would exactly be the complex number multiplication with Euler, let's say, representation. So what exactly happens? Just imagine that we have C in complex numbers, a complex number, complex numbers, this Z, and it could be something like X plus IY, let's say. Theta is just the angle or a real number. For Z, the complex rotation by angle theta would be defined as this equation right here, which is Z times E to the power of I theta, which is Euler representation for complex numbers, as you might know, and which would be the same as Z times cosine of theta plus I sine of theta. And again, as I said, if we imagine Z is x plus iy, if we multiply that to this, it's exactly the same as saying that we multiply this matrix to the vector of xi and x and y. And yeah, that's technically what will happen. And so with a little bit calculation, which I'm not going to go into detail, again, you can refer back to its paper, we can understand that this matrices, and by the way, this sign is element-wise multiplication, this whole, all these matrices, we can simply represent them as this diagonal block diagonal matrix, which each of these are m theta i's can be seen as cosine m theta I minus sine and cosine of m theta I. And we can simply achieve this block, this part, by multiplying this cosine and sine to x1 and x2, let's say, for this case, which again would simply be this equation, the same as this equation right here, because complex numbers are literally the same thing. So an example for that would be, just imagine that we pick d equal 4 and position would be m equal to 1, and we have because we have d equal to 4, so the embedding dimension would be 4, so x would be, let's say, something simple like 1, 0, 0, and 1. So what we need to first do is, first we need to compute the thetas, and again, going back to the equation, how the thetas look like is just simply this constant to the times of that equation, or whatever that is, for I from 1 all the way up to half of the dimension for so in that case, in our case, because these two we only have two in fact two frequencies, or let's say thetas, theta 1 and theta 2, which is theta 1 is equal to 1 and theta 2 is equal to 0.01. Then we need to calculate the frequencies, or let's say angles, which are m theta i's for all m and all thetas. And this is exactly how we calculate them, and we get the cosine and sine of those. Now, what we can do, as I said, we don't need to, in order to achieve this big matrix and big equation here, we can simply put them and divide them 2 by 2 in tuples or pairs. So in our case, since we have x equal 1, 0, 0, 1, we can divide them into 2 tuples or pairs, and then we can literally calculate them with the help of complex numbers, which is technically the same as this matrix here. For the first two, the pair 1 would be 1 and 0, and we can literally multiply them by these cosine and sines, and the same thing for, in order to get x1, rotation of x1 and x2, and the same thing for the second pair, which is x3 and x4. So technically we will do all this for whatever our embedding is. For example, in the case of Mistral, which the embedding, I guess it should be 4096, so we should do all this. We should technically turn this into 2 by 2 tuples and do the same equation for all of them. And this would be the result right here. And then we concatenate these two results, and we will have the final output, as we can see right here. So what we had the embedding right here, which was technically 1001, but now we have this much informative, I can say, if I can finish this. Yeah, we have this much more informative vector which has the positional in fact information of the vector and the token, not only for itself and absolute, but also relative to other tokens, which is very useful in the technically language models. But what this means in the code, so this is the RoPE code from Mistral itself, and you can find all these information, the PDFs and the code itself, in my GitHub repo. I will put the link for that right down below. I just added a little bit more doc strings and also some comments and explanation to understand it easier. But yeah, let's dive deep into that and see what's exactly happening. So the first function, it has two main functions. The first one is just pre-computing the frequencies or the angles, and the second one is applying the rotary embedding. So what will happen in the first function is what we have as input is the dimension, and which end here means the sequence length. So technically this is those m's, and the theta, the constant theta, which you can turn it, but usually typically it is 10,000. So first we can calculate all those frequencies, which this line is technically the same as here, just calculating all these, and then we have all of the m's here because we don't want to calculate them one by one. So what we do, we have all the m's here in a form of a vector, so that would be a vector of from 0 to all the way to t or m, we can say. And then we can do a outer product to get all those, technically right here it would be angles m theta i's for all m's and thetas with this operation, with this line right here. And the shape of it would be end and the half of the dimension. And we can technically turn them into the polar format because we want to have them as a complex numbers for doing the complex multiplication. What next we do, we apply them. But if you remember again from the architecture, what we had here, we need to apply those the RoPE into K and Q. So we will, as an input here, apply rotary embedding. We will have the input tensors of the query and key, and also at the same time the frequencies. So here we can turn in fact query and key into complex numbers to do that complex operation. And remember, the shape of them is the sequence length, badge, and half of the dimension. So it has 3 dimensions, but the frequencies we had, in the frequencies we only had 2 dimensions. So what we need to do, we need to add additional dimension into that in order to be able to match them and do that multiplication easier. So once we turned query and keys into complex numbers and add this additional dimension, what we can do is we can do the matrix complex multiplication and then turn them again back to real numbers. So that would give us the, technically just right here, again back to PDF, doing the multiplication right here and then turning them back into real number, or let's say doing the concatenation, and we will get all the results back from this function, which is, again, we had the Q and K as the embeddings, we applied those frequencies, now we have the positional information for all those tokens. And yes, that's technically it. And the next part would be, technically in our Mistral journey, would be the RMS norm and embedding.